Hello, I'm Seema and welcome to part 12 of the chapter Periodic Classification of Elements. In this video, I'm going to tell you about the F block elements. The F block falls separately in the periodic table. It is these two groups of these actually are 14 groups and two rows of elements that have been kept separately for the sake of making the periodic table a little compact. They actually belong, these 14 groups actually belong between barium and hofmannium and radium and rutherfordium. But since if we did that, the periodic table would really expand far more. Therefore, these elements have been kept separately. Although the first two elements here, the lanthanum and the actinium here, they should be here. And the F orbitals are actually being filled up from cerium and thorium to lutetium and lawrencium. So you could say lanthanum and actinium, they are the D block elements, and the rest, these are the F block elements. But since they follow lanthanum and they are known as the lanthanide series, and this series follows actinium, therefore they are known as the actinoid series. That's the reason why lanthanum and actinium have been put down here, while they actually belong here. And then these 14 elements, they should fall between these two. But the F block has been kept separately, and these two rows are known as the F block elements. Why are they called the F block elements? Because the last electron that enters or is being added up is entering the F orbitals of the inner penultimate shell. The last electron in these compounds is not adding to the outermost shell, nor is it adding to the one shell before the outermost shell like the transition metals. They are adding to the F orbitals of the inner penultimate shell. That is, if it is the sixth period, then cerium, prasomium, in these the F orbitals of the fourth shell are being filled up. In the seventh period, after actinium, where you have francium, radium, where the electrons are in the seventh s orbitals of the seventh shell, in these, the electrons of the fifth shell, the F orbitals of the fifth shell are being filled up. And since there are 7 F orbitals, each orbital has a capacity of 2 electrons. Therefore, you have 14 electrons that fill up. And that's why each of these F block series consists of 14 elements. The first one, mind you, are not actually the F block elements. These are the F block elements. So what is the general electronic configuration of these, the F block? In these elements, n-2, if n is the principal quantum number, the outermost shell, then one shell less than that would be n-1, and another shell less than that, earlier, before that, would be n-2. The F orbitals of n-2 are being filled up, that is, electrons move from 1 to 14 are being filled up here. And in the d orbital, like in lanthanum and actinium, we see it is the d orbital. Sometimes for the sake of stability, the electrons may jump up to the d orbital. You know, where the half-filled and completely filled shells are more stable. We don't go into the details of the configuration, but for 11th and 12th, it would suffice to just learn that the d orbital of the penultimate shell may have one electron here or there. For example, in the case of lanthanum, it is there, which is not actually an F block element, but this can be 0 to 1. And the s orbital, of course, of the outermost shell has 2 electrons. So the general configuration would be n-2 F 1 to 14, n-1 D 0 to 1, and ns 2. These elements, I told you, the S block and the P block together are called representative elements. The D block, on the other hand, are known as the transition elements, because in these the penultimate shell is being filled up. And the one before the penultimate, even inside the penultimate, is the inner penultimate shell. So these, the lanthanide and the actinoid series, or the F block elements, are also called inner transition elements. The actinoid actinoids usually, the early actinoids especially, they are radioactive in nature. And radioactivity is a property by which the substances, they emit light of their own. And if they do so, obviously they lose energy. And if they lose energy, they are very unstable. They could not be stable. We had studied when we did structure of atom that an atom is stable because as long as electrons are in their orbits or orbitals, they do not lose energy. And if they do not lose energy, they remain stable. But these elements which are radioactive in nature, they tend to lose energy and hence are very unstable. And since they are unstable, their study is not easy. And elements after uranium are usually called transuranium elements. And many of these transuranium elements have either been found in traces or they've been prepared in the laboratory in very, very minute quantities. And if these elements are produced, they are not stable enough. You can imagine when you have extremely large shells, the outermost shell, and the f orbitals which are 7 in number, 14 electrons, imagine the amount of repulsion the electrons experience with each other. If you have 94, 95, 96, 100, 112, 130. So elements after uranium usually are unstable or found in very small traces, and hence we've not done detailed study of these as yet. So this was about the F block elements, which are known as the inner transition series. The transuranium elements are only found in traces, and hence our knowledge about them is still not enough. So this was F block elements. In the next video, I'm going to tell you about nonmetals, metals and metalloids. Thank you for watching. Please like my video if it helped you, subscribe to my channel and ask your friends to watch it too, and keep returning for more videos in chemistry. Bye bye.